Hi guys, so let's continue with our part C of the question. Let's continue with this question. Derive from first principles an expression for the effort required to raise a load with a screw jack, taking friction into consideration. So we're required to derive an expression for the effort that is required to raise a load with a screw jack, taking friction into consideration. Yes, so at the back of your mind, you must know that the principle on which a screw jack works is similar to that of an inclined plane, meaning that if you really have some science of the inclined plane, how it really works, then this derivation is going to be quite simple for you. But it's simple. So let's continue. So as we rotate the hand of the screw, we're going to form a complete turn of a screw thread, and this will form an inclined plane as shown. So alpha is the helix angle, and if pi d is the distance traveled by the screw in one rotation, then in that one rotation it will cover a distance of one pitch denoted as p. So meaning that p is pitch. I have said that if pi d is the distance traveled by the screw in one rotation, it means that in that one rotation it will cover a distance of one pitch, which is p. So next, let's have the diagram showing the various forces acting on the screw. This is the diagram trying to show the various forces that are acting on the screw. So P represents the effort applied on the hand of the screw, and it's horizontally being applied, and it is applied horizontally in the horizontal direction so as to lift the load upwards. So W is the weight of the load and it acts downwards, and R is the normal reaction of the load and it's perpendicular to the plane. So on resolving P, the effort P, we have P cos alpha trying to move the load upwards, but it's being opposed. It's being opposed by a frictional force F. But remember, F equals to mu R, and we get this from the definition of coefficient of friction. Remember, mu is the coefficient of friction, whereby coefficient of friction mu is given by frictional force over the normal reaction, and when you make the frictional force the subject, we end up with mu R. Now with all this in place, let's continue with our derivation. So from our first diagram, the development of the screw, which had the pitch and the pi d, it was shown that tan of alpha equals to p over pi d, whereby p is the pitch and d is the mean diameter. Okay, so we have got this expression from our first diagram, which was the development of the screw. So let's go on by resolving the forces along the plane and perpendicular to the plane. So when we resolve the forces along the plane, we have P cos alpha equaling to W sin alpha plus F. I think we can see they are along the plane, but though the frictional force and W sin alpha, they are in the opposite direction to the P cos alpha. As we go further, we get P cos alpha equaling to W sin alpha plus our frictional force is mu R. So let's call this our first equation. Going further, let's resolve those that are perpendicular to the plane. So perpendicular to the plane, we have R and R, the forces that are perpendicular. We have one which is W cos alpha plus P sin alpha. So meaning that, let's call this our second equation. So we're going to substitute our second equation, or r, into our first equation, since we have r, the prefix r in our first equation. So by substituting our second equation into our first equation, what do we get? We get p cos alpha into w sine alpha plus mu. R is this second equation into r, which is w cos alpha plus p sine alpha. We get here p cos alpha into w sine alpha plus mu w cos alpha plus mu p sine alpha. Yeah, so I think we can see that we have some common factors here. Let's collect the like terms together. I'm going to take I'm going to collect the like terms. I have p here, p cos alpha. I have mu p. I can take this to this side and I let this remain the other side. As we collect like terms, p cos alpha minus mu p sine alpha, w sine alpha plus mu w cos alpha. When I pull p outside, we have cos of alpha minus mu sine alpha equaling to, I'll pull out w is common here, w into sine alpha plus mu cos alpha. Making p the subject, we have w sine alpha plus mu cos of alpha over cos alpha minus mu sine alpha. We have to note something here. Remember that mu equals to tan phi, and this is true when we are deriving the limiting angle friction, that angle which the resultant reaction R makes with a normal reaction. Actually, perhaps I'll be making a video for this too, proving that mu equals to tan alpha. But if you read something about the inclined planes, this is very true, that the coefficient of friction equals to tan alpha, and alpha, this is the limiting angle. So in my next step, I'm going to substitute mu with tan phi, and this is what I will create. My p will equal to w into sine alpha plus, where there is mu, I'm going to put tan phi, but tan phi is sine phi over cos phi. This is the same as tan, I think we all know that, multiplied by cos alpha. This is over cos alpha minus sine phi over cos phi multiplied by sine alpha. Hope that's very clear to all of us. So p will equal to w sine alpha times cos phi plus sine phi times cos alpha over cos alpha times cos phi minus sine phi times sine alpha. I believe you can see that in this expression, this cos phi will die with the other one, and we shall end up with sine alpha times cos phi plus sine phi times cos alpha, and also downwards we shall remain with cos alpha times cos phi minus sine alpha times sine phi times sine alpha. I hope we are all together at that level. So as we reach this level, I think someone can see an identity there. I'm saying a certain identity. What we have is p equals to w sine phi times cos sine alpha times cos phi plus sine phi times cos alpha is the same as sine into alpha plus phi. I think we all know that kind of, because this is the expansion of this, right? The same thing applies downwards, that cos alpha times cos phi minus sine phi times sine alpha is the expansion of this, of cos alpha plus phi. And I think we are seeing a turn there. We are seeing sine cos, and the angles are the same, meaning that p w will equal to p equals w tan alpha plus phi. Wow, I'm glad you have reached this point. So I want us to conclude with expanding this expression. I am P equals W tan alpha plus tan phi over 1 minus tan alpha tan phi. P equals W, which is the weight, into tan phi plus tan alpha plus tan phi over 1 minus tan phi tan alpha. So this is the effort required to P. This is the effort required to lift the load. So meaning that from this very equation, the actual effort required to raise the load can be calculated. So P is that. So the question, as it was saying, that from first principles, they wanted us to derive an expression for the effort required to raise the load with a screw jack taking friction into consideration. So meaning that P is the effort that is required. Using this expression, we can generate the effort, that is the actual effort required to raise the load. So that's the answer of our question here. But I want to thank you by adding something in this video, that if you're following up to this level, perhaps some other question could be derive the torque required to raise the load with a screw jack taking friction into consideration. So if they ask you, okay, in this question they've asked us about the effort, which is given by this expression, but in some other person can also ask you to derive the torque. So let me add you with the torque, because deriving the torque, you just have to continue from where the effort ends. So for us to be able to derive the torque that is required to raise the load with a screw jack, what we have to do is we are required to first derive the torque required to rotate the screw. So for the torque required to rotate the screw is given by T1 equals to P, which is the effort which we have been generating, the effort required to raise, times D over 2. Let me explain this. Let me draw a profile. So if the effort P is applied, this is a screw profile. If effort P is applied on a screw, so the distance from the center up to the effort, is D over 2. And this is because we are taking the mean diameter of the screw. That's why we are having D over 2. So meaning that torque T1 equals to P, but P is given by W tan alpha plus tan phi, this very expression, 1 minus tan alpha tan phi times D over 2. But recall D is the mean diameter. Yes, so as we continue next, by uniform wear theory, the torque required to overcome the friction at the cup and the head is T2 equals to coefficient of friction WRM, where RM is the total torque that is required to raise the load with a screw jack taking friction into consideration. Total torque T will equal to T1 plus T2, whereby T1 is the torque required to rotate the screw, and T2, we generate T2 from by uniform wear theory, and that's the torque required to overcome friction at the cap and the head. Yes, thank you very much for watching. We're so blessed. Don't forget to like this video. Yes, we love you all. Fast Lane, creating a path of knowledge. Thank you.